Okay, so today we're going to do section 5.2. Title is Orthogonal Complements and Direct Sums in Rn. Okay, this will be kind of an abstract section, but the stuff that we do here is gonna will show up in the later material. We'll need this stuff for later on. Okay. So remember this whole chapter. This whole chapter is about something called inner product spaces. Okay. And what an inner product space. So this inner product is basically a generalization of the notion of dot product. Okay, so in Rn, you have this thing called the dot product. What we'll mainly use it for is, it gives you a sense of the angle between things, right? Like it's related to the angle between vectors. And in particular, it tells you when things are perpendicular to each other, right? If the dot product of two vectors is 0, then that means that the vectors are perpendicular to each other. Okay. So we're actually going to do this in more general spaces. So you have an abstract vector space, and you want to talk about vectors, those vectors being perpendicular to each other. Okay. So for example, you could have polynomials being perpendicular to each other. Like, so how do you talk about perpendicularity in more abstract vector spaces? Okay. So, but right now we're going to stick in Euclidean space. So we'll start off with one notion, and we'll sort of get rid of this notion pretty soon, but we'll start off with this. So you have two subspaces, so x and y are subspaces of Rn. Okay, and if the dot product of x against y is 0 for every x in x, for every y in y, then we say that x and y are orthogonal. Orthogonal subspaces. Okay, so it's a pretty simple idea, right? You take any vector in the first space, you take any vector in the second space, and they're perpendicular to each other. And if that happens, we say that these guys are orthogonal. And we write that x is perpendicular to y. That's the abbreviation. Okay, so let's do some examples. First example, let x be the span of 1, 0, 0 in R3. So your vector space is in R3. Let x be the span of 1, 0, 0. So it's the x-axis. Okay? All the vectors whose ends lie on the x-axis, right? And let y be the span of 0, 1, 0 and 0, 0, 1. Okay, so y is the yz plane. So here's the yz plane, yz plane. Right, and you see that anybody in x is going to be perpendicular to anybody in y, right? Then any x in x is perpendicular to any y in y, right? Because anybody in x is going to look like x0, 0, and anybody in y is going to look like 0, y, z. Of course, when you dot them together, you're going to get 0. Right? Yes. Okay. Sort of an intermediate example. We could do something a little bit simpler. The span of just 1, 0, 0 is perpendicular to the span of 0, 1, 0. The span of 1, 0, 0 is perpendicular to the span of 0, 1, 0. Right? The x-axis is perpendicular to the, also perpendicular to the y-axis. Right? Okay, so even simpler example. Number 3, let's give a non-example. If I let x be the span of 1, 0, 0 and 0, 1, 0, and I let y be the span of 0, 1, 0 and 0, 0, 1. Okay, so x is the xy plane, right? X is the xy plane here, and y is the yz plane. Right? Y is the yz plane. Then are these guys perpendicular to each other? Are x and y perpendicular to each other? Who says yes? Who says no? Okay, 2 people raised hands for yes. Nobody raised hands for no. Okay, talk with somebody nearby for half a minute.
It seems like just like 2 kids that go like this.
Okay. Okay, so the answer is clear because it says non-example, right? Right. This is not an example of orthogonal spaces. So the answer is no, right? Why is the answer no? Right? To be perpendicular means that everybody in the first space has to be perpendicular to everybody in the second space, right? Can you find 2 vectors, one in the first space, one in the second space, that are not perpendicular to each other? Yeah.
0, 1, 0, 0, 1, 0.
0, 1, 0, 0, 1, 0, right? Yeah. Right, this guy right here, 0, 1, 0 is in both spaces, right? This guy is in both spaces, and it's not perpendicular to itself, right? Right? If you take the dot product of it against itself, you get 1, right? So no, right? This is not an example. Okay, yeah.
And so just to like clarify, if x is perpendicular to y, then y is perpendicular to x.
Yes, yeah. So it's a mutual, it's a mutual thing, right? You don't say, yeah. So right, look at the definition, right? Every x and every y and y have to be perpendicular to each other, right? And there's nothing ordered about this, right? If x t y is 0, y t x is 0, right? So yeah, that's true. Okay. Okay, so we introduced this thing called orthogonal subspaces. We're actually going to almost discard this notion immediately, in case replace it with something more sophisticated. Okay, so let me ask a question first. Are we saying say that x and y are perpendicular to each other? Okay. If some vector z is perpendicular to every x in x, must z be in y? Okay, so you've got these two subspaces, they're perpendicular to each other, and you have this vector that's perpendicular to everybody in one of them. Are we saying that it has to be in y, that it will be in y? Ross is shaking his head from the very beginning. Why not, Ross? Can you give me an example of?
For example, like x is a span of 0, 1, 0, and y is a span of 0, 0, 0, 1, and z is the vector of 1, 0, 0.
Yeah, great. So, so you could have something like this, right? Here is x. X is this axis. Y is this axis, right? But you could have some other vector that's perpendicular. This is your little z, right? Little z is perpendicular to x, but it doesn't lie in y. Okay. However, if we look at this example, and we say, let's look at everybody who's perpendicular to x, right? If we look at everybody who's perpendicular to x here, that actually is y, right? In this example where we've got x being the x-axis and y being the yz plane, right? If you have somebody who's perpendicular to x, well, it's in y, right? Okay, so there's a terminology we're going to introduce. It's called the orthogonal complement. So okay, so you have some subspace in Rn, and we let S perp be everything in Rn such that the collection of all vectors that are perpendicular to everything in S. Okay, the collection of everybody, the collection of all vectors, right? The collection of all vectors that are perpendicular to all vectors in S. Right? Okay, and this thing, right, collection of all vectors that are perpendicular. Maybe it's clear if I say perpendicular to every vector in S. Okay, and this thing is called the S-perp is called the orthogonal complement. Orthogonal complement of S in Rn. Okay, so for, let me ask you a question. Let's say that x is perpendicular to y, that you've got two subspaces and they're orthogonal to each other. What can you say about, it's a little bit poorly phrased, but what can you say about x perp and y perp? What does that tell you about the orthogonal complements? Hold on, Lizzie. So just because you came in late, this means that x, y is 0 for all x in x, all y in y. Okay. So suppose you know that. What can you say about x perp and y perp? Lizzie, go ahead. Since you're
I was going to say that the span of y is part of the orthogonal complement of x.
Well, you don't want to say the span of y because y is already a subspace, right?
Okay, so just y.
Just y.
Okay.
Yeah, y is, so y is then a subset of x perp, right? Because x perp is everybody who's perpendicular to everybody in x, right? And we know that from the statement here, everybody in y is perpendicular to everybody in x, right? So y is contained in x perp, and also we know that x is contained in y perp. Right? Okay, so let me make a bunch of sort of simple observations. So observation 0, say, is that if you have a space and you have its orthogonal complement, well, then they're perpendicular to each other. Of course, right? Right, because by definition, this is the guys who are perpendicular to that. Everybody in here is perpendicular to everybody here. Okay. Second, suppose you know that, well, actually, I should have done this earlier. Suppose you know that two subspaces are perpendicular to each other. Then the intersection is what? Then the intersection is what? If you've got two subspaces, they're perpendicular to each other, then the intersection is? Don't say it out. But yes, the intersection is 0, right? The 0 vector. Right? Because if you're in the intersection, that means that you're perpendicular to yourself. Right? In other words, your dot product against yourself is 0, right? Because then the dot product of you against yourself would be 0, right? Which would mean that your magnitude squared, right? The dot product against yourself is your magnitude squared. Your magnitude squared would be 0. In other words, your magnitude is 0. In other words, you are 0. Okay, last one. The orthogonal complement is a subspace. Orthogonal complement is a subspace. Okay. Take 1 minute and see if you can explain. You see if you can convince somebody else that that's true. How would you show that it's a subspace? Well, you have to show that it's closed under vector addition and scalar multiplication. Right? So think about why that's true. Okay, so let's think. Let's say that x1 and x2 are in Y perp, right? So y is x1 plus x2 in Y perp. Well, what does it mean to be in Y perp? It means that you're perpendicular to everybody in Y, right? So this means that x1, ty, and x2, ty are 0 for all y in Y. Right? And you want to show that x1 plus 2, x1 plus x2 transpose y is 0 also. But that's clear, right? But then x1 plus x2 transpose y is just x1 transpose y plus x2 transpose y. So that's 0 plus 0, which is of course 0. And similarly for the closure under scalar multiplication. Okay, is everybody okay so far? Anybody lost?
Could you rewrite that then statement over there?
You mean because it's too messily written?
Yeah, I just don't know.
It says then, parentheses, yeah. So x1 plus x2 transpose y equals x1 transpose y plus x2 transpose y equals 0 plus 0 equals 0.
Okay, thank you. Okay, let's get on to something maybe a little bit more interesting, which is a theorem called the fundamental subspaces theorem. Okay, and it's not the fundamental spaces theorem; it's the fundamental subspaces. I think this is kind of a poor name, but these guys are grouped together. It's the fundamental subspaces theorem, not the fundamental subspaces theorem. At least that's what I think this title is supposed to be. Okay. Okay, so here we go. If you have a matrix, so let's connect this backwards. If you have a matrix, an m by n matrix, then the null space of A is equal to the range of A transpose Z's orthogonal complement. Okay. So null space of A is the orthogonal complement of the range of A transpose. The null space of A is the orthogonal complement of the range of A transpose. Okay. So now we sort of become a little bit more complicated. And of course, if we replace A by A transpose, you could get something like null space of A transpose equals the range of A transpose transpose, the orthogonal complement. So that's just extra, right? You could have it this way or that way. It doesn't matter. Okay. So maybe think about it for a minute and see if you can figure out why that's true. Actually, the proof is pretty simple. Why is it true that the orthogonal complement of the range of A transpose is the same thing as the null space of A? So think about what the null space of A is. And I'll hand back some homework while you guys are thinking.
Okay, turn to somebody nearby and talk with them about why this is pretty clear.
Essentially, space of A is anything that really takes to zero perpendicular. We'll do that.
Say that. Okay, so does somebody want to talk about this? What does the null space of A have to do with the range of A transpose? Well, what's the null space of A? Null space of A? The null space of A. It's too easy. Maybe you don't want to say it. The null space of A, of course, is all vectors such that this is 0. Right? Okay, so what does that have to do with A? So what does that tell you, right? That if you take, what am I doing? This is 0, 0, 0, 0, 0. Right? So what does that mean? That means if you take A1 through A1, you take the first column against this guy in the null space, you get 0, right? The second column against this, you get 0, right? In other words, so what you see, that if X is in the null space of A, you see that X is perpendicular to every AI, right? Every row. Right. X is perpendicular to every row of A. Right? Okay. In other words, it's going to be perpendicular to everybody. X is going to be perpendicular to every linear combination of the rows, right? Every linear combination of the rows. The span of the AI. Right. But that's the same thing as the range of A transpose, right? The range of A transpose, right, is right. If this is A transpose, well, the range of A transpose is the span of these guys, which is the same thing as the span of the AI, right? So X is perpendicular to every X is perpendicular to every vector in the span in the range of A transpose. Right. Right, so what does that tell you? That tells you that the null space of A is contained in the orthogonal complement of the range of A transpose. Right, because like everybody in here is perpendicular to everybody in here. Right? Yeah, read.
Do you have to prove that in reverse too?
Yeah, you have to do the opposite. You have to do the opposite thing, right? I mean, it's actually kind of the same argument, basically. Right? You say, well, look, suppose let's show that this is contained in this, but it's basically the same argument. You say, well, look, say that so the range of A transpose perp is the set of all x such that x is perpendicular to everybody in the range of A transpose. The set of all x such that x is perpendicular to everybody in the range of A transpose. Right? But if you're perpendicular to everybody in the range of A transpose, then you're perpendicular. It's the same argument, right? Then x would be perpendicular to all of the AI, right? Because the AI, the range of the A transpose, right? So the range of A transpose is the span of the AI, right? So if you're in range of A transpose perp, that means that you're perpendicular to each of the AI, right? But that means that you're in the null space of A. Right, so it's the same thing backwards. Any questions about this? It's pretty straightforward, right? Just understanding what it means to be in the null space, right? Being in the null space means that you're perpendicular to everybody in here, which means that this goes there. Okay, so this theorem, even though it's pretty simple, we'll use it a lot. So try to keep this one in mind, that the null space of A is the orthogonal complement of the range of A transpose. So let me erase here. Some more facts about orthogonal complements. So it's a theorem. If you have part one, let's say that S is a subspace. Say S is a subspace of Rn. Okay. Part one is that there's actually some connection between the dimension of S and the dimension of S perp. Maybe you can guess it. What's the relation between the dimension of S and the dimension of S perp? Hold on. This was hold on. Anybody other than Dan and Reed and Molly and Julie? No, go ahead, Molly.
Is it that it's equal to n?
Yes, that the sum is n. Yeah. they are complementary. Right, was that what you were going to say? Yeah, read. Julian. Yeah, the sum is n. Okay. Part 2, and this is related to part 1, if x1 through xr is a basis of S, and xr plus 1 through xn is a basis of S perp, then you can put those two bases together, x1 through xn is a basis of Rn. Okay. Again, this is a theorem that's not, whose proof is not too hard, I think. So maybe I'll let you think about it. But first, before you do it, let me ask, what does this remind you of? Like, what theorem is this reminiscent of? This is, yeah.
The dimension of the null space and the dimension of, or in the, right?
Exactly, yeah. This sort of screams rank theorem at you, right? Okay, so so think about how to do it using the rank theorem. I just realized that I was considering wearing a Halloween mask today, but I forgot about it. Well, in Japan over the summer, I went to a $1 shop, and they had Buddha masks. Like, you can disguise yourself as the Buddha. I thought it was so bizarre, I had to get one. So my wife suggested I wear it to class. Okay, yeah, so then take a minute and see if you can prove this using the rank theorem. Okay, does somebody have an idea? Does somebody have an idea of how we might use the rank theorem to get something like this? clearly we're hoping that one of these is the dimension of S and the other is the dimension of S perp, right? We're hoping to make a matrix. We're hoping to make a matrix so that the range of A is S. How do we make a matrix such that the range of that matrix is S? Well, go ahead, Lizzie.
Find a basis of S.
Find a basis of S, right? So let x1 through xr be a basis of S. Great, right? And then make a matrix out of it, right? Then let A be the matrix where these guys are the columns. Right? Okay, then of course, S is the range of A. Right? Okay. What about S perp? Well, the range of S perp is going to be the range of A perpendicular. Right? At this point, we pull out the fundamental subspaces theorem. The range of A perp is the same thing as the null space of A transpose. This is the null space of A transpose. Right? And you're starting to see how this fits together. Right? Now, the rank theorem says that the dimension of the null space of A perp plus the dimension of the range of A perp is equal to n. So what do we get? We get that the dimension of S perp plus the dimension of S is equal to n. Right, notice that this guy is an n by R matrix. Right, A is an n by R matrix. A transpose is an R by n matrix, right? So that we have the right size when we look at the transpose. Okay. Ross? No? Okay. Okay. Now there's one thing that I sort of slid over, which is that the dimension of the range of the transpose and the dimension of the range of the original thing is the same. Remember, we did this, the column space and the row space have the same dimension when we were talking about the rank. Okay. So, right, you might be saying, what? You know, how did he replace that with the dimension of S? Right? This is RA transpose, this is RA, right? But the dimension of RA is the same as, so maybe I should slow this down a little bit. Say this is the same as the dimension of A, right? But this is the dimension. Oops, this is the dimension of S. Okay, so the dimension of the subspace and the dimension of its orthogonal complement are complementary to each other. They add to n. Let me try to quickly get the second proof. Why is it true that if you have a basis of S and a basis of S perp, and then you can just put them together and get a basis of Rn? So, well, it suffices to show that this whole collection, x1 through xr, xr plus 1 through xn, are linearly independent. Right? because there are n of them, right? And we're in Rn. And we had this theorem that said, if it's linearly independent, it'll be spanning, and if it's spanning, it's linearly independent. You don't have to prove both of them. You can only, if you know the size already and you have the right number of vectors, then you just have to prove one of the qualities of the basis, right? So you have to see that they're linearly independent. So you say, okay, well, suppose that, C1 x1 plus CR xr plus CR plus 1 xr plus 1 plus Cn xn equals 0, the 0 vector. Okay. I want to see that all the coefficients are 0. Okay. We play a trick. We move everything from one basis to the other. We keep the bases. We separate. We keep everything from one basis on one side. We move everything from the other basis to the other side. Okay, and we say, well, look, this thing here is in S, and this thing here is in S perp, right? So this thing, I don't know, we call it V, say. This thing, whatever it is, it lies in S perp, but it also lies in S. Right? Well, if it lies in S and S perp simultaneously, it must be 0. Right? So what does that tell us? That tells us that C1, X1, that the left side and the right side are both 0. Right? The left side and the right side are both 0. At this point, we use the fact that these are bases. This thing is a basis. X1 through XR is linearly independent because it was a basis of S, and these guys were independent because they're a basis of S perp, right? So that tells us that C1 through CR must all be 0, and it tells us that CR plus 1 through through Cn must also be 0. Okay, so all the coefficients are 0. Okay, that's it for today. Yeah, this section is sort of, it seems kind of odd, right? There's these bits and pieces of things and you're not really sure what we're going to do with them. But we will, as you might guess, we will definitely use them later. But yeah, it doesn't really form into a cohesive story or anything.